So it's a talk about living without Beth and Craig, about explicit definitions and interpolants in DLs with nominals. We have a few more results now also on DLs with role inclusions, and I'll talk about them as well. And it's joint work with Alessandro, Jung, Andrea, and Anna. Okay, so I'll mainly talk actually about explicit definitions and only in the end a bit about interpolants. So what is our question? We have a description logic L, an ontology in L, a concept name or nominal A, and a set of symbols, concept and role name sigma. And the question we want to answer is there a definition of A in the language L sigma? So we can use all constructors of L and the symbols in sigma. And that means that we want that O implies that A is equivalent to D. Well, this is sort of, I think, a fundamental question from a DL viewpoint. Here are concrete applications. In 2006, in a Tentate et al. Paper, the question was raised how to extract an acyclic terminology from an ontology. So how to transform GCIs into concept definitions. Another application, and there was a talk here yesterday by David, is to FO rewritings. So we can use, in some cases, explicit definitions to obtain FO rewritings. And then I want to emphasize that we don't only deal with definitions of concept names, but also individuals. And then what we get are definite descriptions or referring expressions. And again, there will be a talk tomorrow related to this. We are mainly interested in the decision problem in this talk. Of course, there are other questions. What is the size of definitions? And if there is one, how to compute it? The techniques we have should help with that, but I won't really talk about it. So there is really not any work on this question. And the reason is that very often it's not a very interesting question. Namely, if the logic we are dealing with has the projective best definability property, or PBDP. What does it mean? It means that a concept name or individual is explicitly definable if and only if it is implicitly definable. I write here only one arrow because the arrow backward is trivial. And so if we have this property, we have to check implicit definability only. And what does it mean? It means that the extension of A is uniquely determined by the ontology and the signature sigma. And we can actually write this up as a subsumption problem. So here, O sigma is obtained from O by replacing the non-sigma symbols by primed version. And then A is implicitly definable if and only if from O together with O sigma, we obtain that A is equivalent to A prime. So if a logic has this projective best definability property, then explicit definability can be decided using your favorite DL reasoner. It is not more complex than that. It is not really a separate research problem. So for ALC, ALCI, ALCQ, ALCQI, and so on, many DLs enjoy this PBDP, and so explicit definability in this case is X time complete simply because subsumption is X time complete. Nothing to do. Now, there are, on the other hand, quite a few DLs that do not have the PBDP, and the one we are mainly interested in here are those with nominals. So ALCO or any extension with nominal doesn't have the PBDP. So implicit definability is not the same as explicit definability. And so we have a research question here. How hard is it to decide explicit definability then? We also look at ALCH, which is known not to have the PBDP, and we go up to ALCHIOU. We could go a bit further. I'll comment on that in the very end. Okay, so here is a simple example illustrating why ALCO doesn't have the PBDP. This ontology says that A is reflexive, R reflexive. And in fact, you can show that A, this individual A, is the only node that is R reflexive. So it is implicitly definable, or actually explicitly definable then in first order logic as the only R reflexive node. But in ALCO, you can't define this even using A, so it's not explicitly definable. So in general, you don't have to work hard to find this kind of examples. So it's not really an obscure thing to hit upon. Okay, so here is then the main result of this paper. Explicit definition existence is 2x time complete for any DL containing ALCO or ALCH and contained in ALCH IOU. So there is good news here. It is still decidable. It was quite possible, before we looked at it, to be undecidable. There's in a way also bad news. It's one exponential harder. It's also interesting news because it shows that Beth really helps. There is no reduction to subsumption, at least no polynomial one. I find it really interesting in the sense also that it shows that the space between implicit and explicit definability is much harder computationally than the space for implicit definability. The lower bound even holds if we look for a definition of a nominal using any symbol distinct from that nominal. So without any restriction on sigma. And in fact, the ontology O we construct there is a knowledge base with only one individual. So there's no other individual needed for the hardness proof than just that individual A. So we are asking then for an ALC definition of an individual. I won't say much about the proof, except that I like it very much. It's based on a bisimulation criterion. So we are looking for bisimilar models. And we do this using a mosaic-based approach, in a way rather elementary. It's not long, the proof. It's easy to understand, but it's based on I think, one really new idea. Take a look into the paper here. I want to move on with the story here. If you see this lower bound for the special case that sigma is every symbol except A, the question, of course, arises, what happens if we look at a concept name under this condition? So what about explicit definition of a concept name A using any symbol distinct from A? And it turns out that this special case, which is of interest if you are looking for a concept definition, so for an acyclic terminology obtained from an ontology, then this is enough. For many other applications, it's not, but there are these cases. So what happens in this case? And the answer is the situation is very different. Because in this case, we can apply the so-called non-projective or simply best definability property, which means that sigma is this full signature except the symbol we want to define. And in that case, many more DLs have that property. So ALCH, we have seen for that ALCH, we have 2x time completeness for explicit definitions in general. But here it has the BDP, ALCIO has the BDP, ALCOU has it. So for these languages, we then get from the best definability property that it's in X time to decide the existence of a definition. ALCO does not have this BDP, but still we get an X time upper bound. So for all the logics we consider in this paper, we get X time completeness for this special case where we allow any other symbol. So I find this quite surprising that nominals behave differently from concept names under this special condition. Right. Let me now move to interpolation. The second part. So let's read this in the form without ontologies. So we just have a subsumption CE1 included in C2. And we ask ourselves, is there an interpolant, meaning that a concept D using only the shared symbols of C1 and C2, such that C1 is included in D and D is included in C2. And we extend this here with ontologies in the natural way. So again, an existence question. And again, not too many people have looked at it because they always focused on the Craig interpolation property, which gives the existence essentially the decision procedure for free because it is a reduction again to subsumption. So the Craig interpolation property tells us, well, there exists an interpolant for C1 included in C2 if and only if C1 included in C2 follows from the ontology, or we were forgetting about the ontology, from the antiset. So again, interpolant existence is not harder than subsumption in the underpinning logic if we have Craig interpolation. Now, a few general comments. Craig interpolation implies BDPT, and explicit definability is polynomial time reducible to interpolant existence. So what we are dealing with when we look at interpolants is the harder problem in many cases than the best definability. Right. It turns out that for the logics we are looking at, we get exactly the same complexity results. So 2x time completeness for ALCO and ALCH up to ALCH IOU for interpolant existence. And in fact, what we do is we prove the upper bounds for interpolant existence and the lower bounds for explicit definition existence. Of course, again, many logics have this CIP, ALC, ALCI, ALCQ, and so on. And for them, we get an X time upper bound from the complexity of subsumption. So same story really as for explicit definitions. Life becomes much harder without Craig and Beth. Right, I want to discuss one application of interpolants. There are, of course, many more, but this one was actually the trigger for us to look into the problem at all. And it is supervised learning. So what is supervised learning in the context of knowledge bases? Well, we have a knowledge base. We have a set of positive examples, P, a set of negative examples, N, and the signature sigma. And we look for good generalizing sigma concepts that separate P from N. So in other words, K implies CA for A in P for the positive examples, and K implies the negation of C for all negative examples. That's the property of a separating concept. So Jung was talking about this yesterday. You could also formulate this here as K doesn't imply CA. Then that has nothing to do with interpolation. So we get something that is very close to interpolation under this strong notion of separability. And in fact, what turns out to be the case is that one can construct an appropriate ontology and concepts such that C separates them. So is a separator or is possibly a good concept if and only if C is an interpolant for the corresponding constructed ontology and concepts. So these ontology will typically contain nominals because we somehow have to encode the knowledge base. And that's how we got into asking ourselves, how complex is it to decide interpolants? Because we needed this interpolants for logics without the interpolation property. So yesterday, as I said, Jung gave a talk on the context for this. I find it actually quite nice and interesting and potentially with lots of scope for future research that a very old notion like interpolation, 70 years old in logic, is so closely related to supervised learning in the open world scenario. Right, let me close with a quick discussion. So interpolant existence and explicit definition existence without Craig and Beth are, as far as we know, new questions. There are, of course, always exceptions. For example, LTL. LTL doesn't have the Craig interpolation property. And it was only proved in 2016, highly non-trivial, that the existence of interpolants is decidable. Actually, they don't talk about interpolants there. They talk about separating regular languages using FO expressions, but it's the same thing. And we looked at the guarded fragment with Jung and proved that it is triple exponential time complete to decide interpolants and explicit definitions there. So also one exponential harder than reasoning. There are, of course, now lots of questions. What about more expressive languages? Interesting candidate to start with would be ALCOIQ. Is that still decidable? Is that undecidable? Or more generally, are all natural decidable DLs? Can you decide for all natural decidable DLs, interpolant and explicit definition existence or not? We don't yet have an example, a natural one for which it's undecidable. And then, of course, the size question, succinctness question for interpolants and definitions, and the more practical questions of how to compute them if you know they exist. And with this, thank you. Any questions?